Syzygy, episode 56, No Bang for Betelgeuse. And welcome back. Welcome back. We've been away for a little while. Back for another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at the table in her office, as ever, Dr. Emily Brunsden. Hi, Emily.
Hello, hello.
Where have you been? It's been Christmas and New Year. We've both been away, but some of us have been more away than others.
I went on holiday.
Yeah. Where'd you go?
I went to Tenerife.
Very nice.
Fantastic.
Tenerife. Now, that's one of those places in the world. There are a bunch of places in the world where I don't actually know where they are. Right? I've got this mental image of all of these little places. Tenerife's an island, right?
Yes, yep.
And to my mind, they're all sort of clustered together off the coast of Europe broadly. But that could be literally anywhere, and I could be off by an entire hemisphere.
I think you're off by a continent here, Chris.
I literally do not know where any of these places are. So Tenerife, where is that?
Tenerife's part of the Canary Islands, which
is
are
where?
kind of to the left of Africa.
Right. My apologies to everyone who lives there and geographers everywhere. And nice place to be at Christmas time.
Beautiful place. Mm-hmm. Yeah. So we went basically because I wasn't going to New Zealand this Christmas. I usually do, to get some lovely summer sunshine. Mm-hmm. And I said, you know what? I don't really think I can do this whole UK darkness thing for an entire season of winter.
Good choice. Speaking as someone who has, it's quite a long dark season.
So to get my vitamin D levels up, went for a week and enjoyed the sunshine. It was a very pleasant sort of 20-ish degrees. Beautiful, beautiful country to do walking in. We climbed up almost anything and everything we could find to climb up. It was just amazing.
Very nice, very nice. And you come back happy and healthy and full of vitamin D and ready for the new year.
Indeed.
Yeah. And we are back with another new year of Syzygy podcast. In this episode, we're going to be talking about something which kind of hit the papers a little while ago. I saw a few news stories on this one about a particular star with an interesting name, quite prominent in the night sky, which has been doing some weird stuff. And people have been looking at it and going, well, clearly that means it's gonna explode in a huge supernova, and that'll be amazing. Turns out maybe that's not quite right. We're talking about the star Betelgeuse. Emily, what's going on?
Yeah, so Betelgeuse is one of the brightest stars in the sky. It's a very, very easily identifiable star in the constellation of Orion.
Okay.
So it's a great one to go out and have a look at, and we'll talk about kind of where it sits and how you can observe it.
And it is easily seen, like it's a big, bright one.
It's really, really easy to see.
Yeah. Which, like in Orion, which bit of Orion is it?
So it's kind of the left shoulder.
Left shoulder, right. So it's not the belt, it's not the sword, it's the shoulder bit.
Well, the left shoulder, I'm not very good at this. So the left shoulder of the left-hand side shoulder.
Right. As you're facing Orion, so stage left.
So Orion, it must be his right shoulder.
Right. Orion's right shoulder, but as we look at it, it's on the left. God, that's confusing. Did you have the same problem that I did when you went from South Hemisphere to North Hemisphere? That, of course, you're facing a different way. Everything's upside down, including things like Orion, where I didn't know that that's what Orion was. Like I'd been looking at the wrong, like Orion standing on his head and thinking the different bits were different bits. It's the same with the moon, right?
Yes,
you look at the face, the man in the moon, and I had a completely different idea of what the eyes and the nose and the mouth were for the man in the moon. And when you come to the northern hemisphere, you go, I see, I get it now. That's what everyone else has been saying.
I get a man in the moon in the southern hemisphere. And
then I do.
And people say that there's a dog in the northern hemisphere. I've not seen a dog.
The dog in the moon in the northern hemisphere?
Yeah.
Really?
Yeah.
No, I haven't seen that.
Some dog playing with a ball. I don't know what's going on there.
They don't know what to... Anyway, that's aside. Tangent, pull it back. Betelgeuse, we're talking about.
Yeah.
You were telling me earlier that you have observed Betelgeuse recently.
I have observed it.
Do you want to just share that with us?
Yeah, it was a very unprofessional observing session in the sense that it wasn't done under a telescope. Mm-hmm. It was done by me sitting in a nice spa pool in Tenerife looking up at the beautiful clear night sky.
Have I ever told you how much I really don't like you sometimes? Yeah, okay. But was it nice?
It was fantastic. Mm-hmm. But you can clearly see that Betelgeuse is not as bright as it used to be.
No, okay, with the naked eye.
With the naked eye.
You can look at it as an astronomer. And I know, okay, don't write to me. I know that all astronomers aren't out there every night doing astronomy things by looking with their eyes at the sky. That's not how it works. But you can look at Betelgeuse and go, you know what? Kind of feels like it used to be brighter.
Yeah, exactly.
Whatever happened to the Betelgeuse we had before the war? Is that, over what kind of time period has it changed?
So from October last year, October 2019 to December 2019, it's dimmed by about 2.5 times its normal brightness.
That sounds significant.
Yeah.
Wow. So you could see that yourself with your naked eye. So people have observed this, and that's caused quite a few people in the world to go, well, that means what? What's the gossip?
She's
going to
blow.
She's going to go. Everyone take cover. Hide under a desk. No, under a doorway. You should be in a doorway. No, that's earthquakes. What do you do for a supernova?
Nothing.
Say goodbye.
Yeah. Get out your camera. It's about all you can do.
Yeah.
So it's true that Betelgeuse is about to explode.
Okay.
But
should we be worried about that?
This is the astronomical about to explode.
Okay, so this is about with an asterisk, and you look down to where the asterisk is, and about means within the next week, month, year, century, millennium.
Our best guess is in about 100,000 years' time.
Sorry. 100,000 years, which, okay, yes, in a universe where millions of years, billions of years are the kind of, time-based currency that we're talking about. 100,000 years is nothing. Like, that's about to go. Any 100 millennia or so now, that's longer than sort of, human prehistory. So we're not particularly worried about this. But at the same time, neither are we out there going, come on, I want to see this for myself when it goes. You'll be waiting a long time, probably, statistically.
Indeed. So we can put some numbers on this dimming. So we do actually have a measurement tool that we use for brightness. And the most common one you're going to come across is the magnitude scale. And this is particularly apparent magnitude. So this is how bright all of the stars are in the sky and give them a number of brightness. And the magnitude scale is a bit crazy. It's one of these hangovers in astronomy whereby astronomers just gave up on SI units, or at least SI units gave up on astronomy a long time ago.
They diverged. They went different paths.
So we have an absolute apparent magnitude scale, which goes in reverse logarithmic numbers.
Right.
So that means that larger numbers, or larger, more negative numbers, mean a brighter object.
Larger, more negative numbers mean brighter.
Yes.
Well done.
And larger positive numbers mean fainter.
Yeah. Can I offer a piece of advice to astronomers everywhere? Just reverse that and everyone will be happy. Like, surely this is the bane of every astronomy student's existence, that they have to figure this nonsense out.
Well, it's kind of made sense because we never really intended to have negatives. The intention of the apparent magnitude scale was we'd put 0 at the brightest star in the sky, and then everything would just be bigger than that because everything's fainter than that.
Kind of feels like that was short-sighted, though, don't you? Well, let's put 0 at, nothing could possibly be brighter than that thing that I've just observed. Oh, it turns out there are a lot of things brighter than that.
Yeah.
We just hadn't seen them yet.
So it's been recalibrated, the scale, since. Right. So there are a few stars that are negative. Not very many, to be fair. But it kind of makes sense that it should work by that fainter stars get bigger numbers, because you keep increasing the ability that you have to see fainter and fainter things. And if you had to redefine your scale every time to be 0 for the faintest object that you could see...
You've got the same problem.
Yeah. That would be annoying.
Yeah, or you'd be going way down into the negatives that way. Anyway, so, okay, all right. You've convinced me that it's not as crazy as it sounds. Still doesn't sound ideal, but fine.
So let's give you some ideas to calibrate your number scale. So about 0 is about the star Vega. It was kind of supposed to be Vega, but Vega's not quite 0, but it's about...
Ish. Let's say Vega-ish. And where do I find Vega? Is that familiar to me? Should be, maybe?
It's in Lyra.
But it's a prominent star?
Yes, it's quite a bright
People
star.
know Vega. Okay. Those of you out there in listener land going, yeah, Chris, come on, Vega. Okay, all right, sorry.
Well, I'll give you another one. Okay, so the brightest star in the sky, apart from the sun, is Sirius, which is at minus 1.46.
Okay. So did you say that's the brightest one in the
That's the brightest
sky?
star,
okay.
yeah. So Sirius is quite close to Orion. It's the dog star, if you like, the part of the Canis Major, who's following Orion on his hunting journey. And what else? So Venus is a bit brighter again. It's minus 4.2.
Yeah, not a star, but still up there in the skies and very bright. Yes. And it's minus...
4.2.
So it's not as bright as Sirius.
No, it's brighter.
It's bright because it's minus 4. Sorry. Yep, wrapping my head around this. Yeah.
And so what the stars that you see on a clear night, on a sort of from a city-ish location, you're probably looking at stars down to about -2, maybe -3 if it's quite a bit darker. If you go to a really nice dark sky, and that's when you start to see the thousands and thousands of stars, and actually constellations even become very difficult to pick out. You're looking down to something like +6.
Right. Or up to +6, so in the direction of fainter stars. Yes, I mean, those are the views that really take your breath away, is when suddenly just the sheer enormity of number of stars in the sky, all the little faint ones that you never knew were there, and they're just everywhere. So many stars. Yeah.
So Betelgeuse has changed by a whole magnitude, basically.
Wow.
So it's gone from 0.5, so quite bright, to 1.5.
Right, 0.5 to 1.5. So it's
a change of 1.
Changed quite a lot. Okay.
But 1 doesn't sound like a lot, but then on a logarithmic scale, 1 is about 2.5 times brighter.
Okay, yes, right. So that's a significant change. It's easily observable, even with just the naked eye. And why? Why would that be happening? I mean, you said a minute ago that Betelgeuse is going to, any 100,000 years or so now, is going to explode. But is it related to that, or is it something else? Do stars just do this?
It is related to that. So Betelgeuse is a really interesting type of star, and it's probably best to start with, let's see what we understand about Betelgeuse so that we can understand why it might be doing this crazy stuff now.
Makes sense.
Even backtrack again. Let's look at Orion, the whole constellation that Betelgeuse sits in, because that's the story of Betelgeuse as well. So the constellation of Orion, as we draw it in the sky and say, these are the lines that connect the different stars and make this particular shape of a hunter, it's kind of one of the best constellations in some senses.
Okay.
To convince you that the shape is what it's supposed to be.
Okay, talk me through that.
I think a lot of constellations you sort of look at and it's like, these 3 stars make a horse.
Oh, I see what you mean. Yes.
And you're like, yeah, really? Okay. But Orion, I can get on board with Orion because it's kind of got this quadrilateral shape. So you've got 4 stars that define the 2 shoulders and the bottom of the tunic of Orion.
Or the belt, I've always thought, isn't it? The belt going
across? The belt is in the middle.
Oh, right, yeah.
So
gotcha.
So you got sort of a box which is 4 stars, and those are quite bright stars, so they're quite easy to pick out. They've all got wonderful names. So Betelgeuse is, I'm going to go with if you're looking at it from the sky, the top left one, then and this is from the northern hemisphere, so Orion's upright. If you're in the southern hemisphere, you've got to turn everything.
Yeah, just stand on your head.
So Betelgeuse is on the top left. The one other shoulder is called Bellatrix. It's not quite as bright as Betelgeuse, but it's prominent enough you can spot it out. The bottom left part of the tunic is called Saiph.
Saiph, as in spelled how?
Saiph. I might be saying it wrong.
Yeah.
But yeah, and that's a bit fainter. And then the other one on the bottom right-hand side of the tunic is Rigel.
Rigel, yes. So 3 out of 4 of those I've heard of.
Right.
2 out of 4 of those I've heard of because their association with movies, because there was obviously Betelgeuse, the movie, spelled differently. And then Bellatrix was one of the bad wizards in Harry Potter, I seem to remember. So yes, but Saiph and Rigel? Right. One of those.
We'll go with either.
Okay, so those are the 4.
So Rigel's actually the 6th brightest star in the night sky. And Betelgeuse itself ranges anywhere from 10th brightest in the sky to 23rd.
Right.
Which is what currently kind of is.
Depending on what's going on.
So these are all prominent stars. And then you've got the 3 stars in a line, which have become the belt of Orion. And then there's kind of 3 stars which hang down from the belt, which we interpret as being a sword. So, of course, the 2nd star in the sword is not really a star at all. And it doesn't take much. You can even, if on a really good, clear night, see yourself that 2nd star looks a little bit fuzzy. But that 2nd star is not a star, it's the Orion Nebula.
Ah, okay.
It's one of the most famous astronomical images. It's a really close by nebula where we have a great star forming region.
Check the show notes because we'll have pretty pickies.
Yeah, it's really fantastic. And then the whole of the Orion kind of area, if you imagine that the Orion Nebula is just this tiny little blob in the middle. If you actually look with really, really good, long, extended photography, there's a huge amount of nebulosity all throughout the entire constellation. It's absolutely huge.
Right, okay.
You can find all sorts of wonderful things in there, including things like Barnard's Loop, which is an enormous big arc of nebulosity that goes through the entire constellation of Orion. There's just a lot of fantastic stuff going on. And the reason is because not only is Orion, or the Orion region, really active in star formation, it's one of the biggest star-forming regions we think in the galaxy.
Wow. Now, just back up a minute, because I always thought that one of the really interesting things about constellations, which are, let's face it, random collections of nearby stars in the sky as we see them. But I mean, if you were to go to some other part of the galaxy and look around, you would not see the same shapes in the sky because the stars, like it's not a plane. They're in 3D space. So the stars that you're talking about in Orion, how close are they actually? They could be incredibly far spread apart, but are you talking about bits which are sort of actually all in roughly the same kind of bit of space? Yeah, so
many of these objects are really associated, truly.
Wow, okay.
So we call like a constellation something called an asterism, which means basically just, well, you see 3 stars in a row, for example, in the belt, but are they actually anywhere near each other truly in space?
Yeah,
Is
one could be really
far
close,
away and one really close. Yeah, so and actually the stars in the belt are not very well associated. They're just randoms. But things like Betelgeuse, Rigel, and Saiph are all pretty much between 800 and 1300 light years away. In fact, Bellatrix itself is the weird one because it's a bit closer at 250 light years.
Right.
So they are kind of part of this giant sort of bubble region of Orion. They weren't necessarily born like in the same cloud, but they're associated with the same kind of big structure.
Okay, cool.
In fact, we maybe think that Betelgeuse was kicked out of a closer structure because it's got this incredible space velocity, its own motion through the galaxy that would only have come about if it's been kind of a bit fussed with in the early part of its life.
Cool. Okay.
So most of them, something like 700 light years away, which is pretty close. So we're really lucky to have the Orion Nebula because it tells us a lot about star formation and it's nice and close, easy to observe.
Yeah. So Orion, beyond being just a particularly good constellation, is actually a very useful thing to look at.
Yeah.
Okay.
So Betelgeuse itself, within the constellation Orion, is something called an M-type red supergiant.
All right, unpack that for me. M-type red supergiant.
Well, we can start with the Betelgeuse and Rigel. They're 2 of my favourite stars in the sky because they are stars that are so bright we can actually start to interpret their colour just with the naked eye. So Betelgeuse, for example, is one of the reddest stars that you can see in the sky, and Rigel is one of the bluest.
Right, that's why I've heard of Rigel before. Yes,
yeah, and they're really handy because they're right next to each other, so you can observe them at the same time.
Yeah, so if you're ever talking to someone about, hey, did you know the stars are different colours? Look, up there, that one, red, blue. See? Done.
Yeah, exactly. Very so nicely that Betelgeuse is a red supergiant and Rigel is a blue supergiant.
Yeah, handy.
Yeah, so a red supergiant means that, the red is kind of self-explanatory. Supergiant gives you a hint of what's going on here.
It's big.
Yeah, this is a star that used to be an enormous blue supergiant, actually. It probably used to be an O star, which is the hottest classification of stars that we have. And it's evolved from that. It's gone through its fuel source, exhausted all the hydrogen in the core during hydrogen fusion to helium, and it's now turned into a red giant star. And it's so big, in this case, we call it a red supergiant.
Right. How supergiant is supergiant in sort of in comparison to something that we know, which is us and our sun, the solar system.
It's quite big compared to you, Chris.
Well, okay, I didn't mean quite that personal. Even though I am quite a large man. Our solar system,
yes,
the sun and the earth. And so how big is a red supergiant?
Well, rather large. So these things are notoriously difficult to measure the radius of, but because Betelgeuse is so close, we've had a pretty good crack at it. We can actually see the disk using really sophisticated interferometry.
Really? You can actually see the size of the star.
You can see the disk. Now, we go on a lot about how you just can't resolve stars. You can't resolve stars.
Stars are points. You can't. Apparently, you can.
You can for very close, very big ones.
Yeah.
And Betelgeuse is one of them. So our best guess is that if you put it in Betelgeuse in our solar system, the edge of the star would be somewhere between the asteroid belt and Jupiter.
What? I thought you were about to say the edge of the star would be sort of somewhere towards Earth-ish. But no, you're talking like past Mars,
Way out.
past the asteroid belt and on its way to Jupiter. That's super giant. That's really, 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 really big.
Yeah, we weren't kidding.
Wow. Okay, I've just completely recalibrated my notion of what that bigness means. Thanks.
It's really, really crazy. Yeah, so that's about 4.5 times the distance from the Earth to the Sun.
Wow. The sun's really looking kind of small now, and we think it's big. Okay, so that's Betelgeuse, red supergiant. Good?
Yeah. Now, the interesting thing about that is even though it's so huge, it's only about 12 times the mass of the Sun.
So it's really big, but really spread out.
Really spread out, yeah.
Wow.
And this is what we call red giants because when you lose the ability to undergo the hydrogen fusion at the rate that you do when you're in your normal fusion state of a star, we call it the main sequence, then your core starts to contract and it does also, you can't hold on to the outer atmosphere of the star so tightly as it used to.
And it's being sort of blown outwards by the radiation pressure that's coming from the reactions in the core. So the outer bits, but they're not being held on as tightly. Why are they not?
So it's kind of puffs up because you've got a contraction of the core, so you've got a change in the distribution of mass.
Right.
And then you're right, and the whole radiation pressure increases at the same time.
So it changes that balance, and then that's quite a significant change in balance to grow to that size.
Yeah, it's quite crazy what happens. So we start, instead of having the fusion reaction of hydrogen to helium in the core, we can trigger, once you get to a compact enough core that gets to an extreme temperature, that helium itself can ignite in fusion, and that helium starts to fuse to carbon and oxygen.
That's where you start making those much heavier elements down in the core. Yeah.
And all of these new nuclear reactions output enormous amounts of energy. And you've still got hydrogen fusion going on. It's just happening in a shell now around this helium fusion core.
Right.
So it becomes just this crazy nuclear runaway reaction, basically.
I'm still about 3 minutes back. I'm still trying to wrap my head around a star that's that big. But okay. All right. How big's the core at this point?
Oh, well, I don't know the numbers. I haven't got them to hand, but it will be a huge core because it's much, much more dense in the core. So when you start with an amount of star, if you like, the size of your core depends on how much gravity you can compress material down to be at your 10 million degrees so that you can start fusion. And the more gravity you have, the more mass you have, the bigger your core that goes along with it. Yeah.
Okay. Still wrapping my head around this one. Carry on.
So you've got this, so the whole star expands basically. And this is the weird kind of contradiction of red giant stars. At the same time, they get brighter, but they also get cooler.
Brighter but cooler. Okay. So the brightness, correct me if I'm wrong, okay? I'm just going to swing this one off the top of my head. The brightness is the amount of radiation coming out, the amount of light across all the different wavelengths. The temperature is the frequency of that light. Where's it peaking at? The color, basically.
Yep.
Yeah.
And we're talking about the surface at this, because that's where we see what we see of the star. We see the surface.
Yeah, we see the stuff coming out.
So the whole star's expanded, which means that the surface has got more rarefied. And it's cooled, even though there's now enormous numbers of photons pouring out of the star.
Right. Okay. So very, very bright, but not as hot as, say, our own sun. Yeah. In the sense of the energy of each one of those photons that's coming out is a higher frequency, shorter wavelength for our sun than for a red supergiant.
Exactly. Okay. Yeah. But we have to remember that surface, right? And inside the core, of course, it's insane temperature.
Crazy,
still.
Nuts. Okay. Yeah.
So that's why we call these big red supergiants. They're big, puffy, red things. And they go through all these wonderful kind of phases. They get really unstable. All these nuclear reactions start getting faster and faster and faster. This is a complete chaotic system for the star. There's just no way it can recover from this state. So very small instabilities inside the star can cause massive chaotic effects on the surface. And this is related to why Betelgeuse is doing such crazy stuff now.
Right.
So it's got this really complex asymmetric sort of envelope that's around it. And that's created by the old outer layers of the star. It's kind of shedding stuff, but it's not a constant stream of material flowing off the surface. It happens in bouts and in phases, and it can happen in one direction more than another direction. So the whole thing gets really, really messy. And you get this really extended kind of emission coming from the whole area around Betelgeuse. And this is one of the reasons why it becomes really difficult to measure its size even, because...
So what does that even mean
yeah,
under those
it's not even really a
circumstances?
sphere
like
anymore.
measure it today, tomorrow is something really different. And I mean, that's the, to me, really fascinating thing about all of this is that like these are changes that are happening across days, weeks, months. It's not, hey, we observed it 100 years ago and now we're observing it and it seems to have changed. It's no, this is changing on our timescales pretty quickly, which is amazing for something that
it's
big.
Incredible, yeah. And this is also why I love pulsations. And incidentally, Betelgeuse has pulsations. We understand that these
This is your home turf. This is what you do.
Yeah, the red giant stars have pulsations, and Betelgeuse is no different. We don't really know much about Betelgeuse's pulsations. We think that they're very long, period, because it's such an enormous star. But it's probably got some sort of fundamental pulsation that's maybe 1,000 days, maybe a bit more.
So
long.
why is that so uncertain? You're sort of, you're talking about this like, well, we're not really sure. And I would have thought it's really close. You can see it, Emily. You can, you said you could actually see the disk of it. I would have thought, well, surely that's a really good candidate. So, okay, let's lock onto that and really measure the hell out of this thing and we'll understand it really, really well. Is it because it is so big and so chaotic? Yeah, we could observe it. It doesn't mean we're necessarily going to understand it in any hurry.
It's part of that, but it's also because, well, first of all, things that are a couple of 1,000 days long, that's a few years, and it takes a long time to get good data on those.
Okay.
But even putting that aside, this is such a chaotic star that when you've got material that can come in and obscure the light, it's just kind of the old sheddings of the star. How do you know whether that's part of the pulsation or if that's part of the shedding?
So it's just a bit too complicated.
Yeah. And
you want a simpler system.
We've got bright spots that appear on the surface that are not, well geometrically distributed across the star, so they cause kind of inconsistencies in the brightness. It's really messed up.
It's just too big and puffy and wobbly to really get a good grip on.
Yeah. So when we think about why we're seeing this particular dimming, there's a couple of options. So I've gone and read a few of experts' opinions about what this might be, and it may well be actually a combination of several things. So it could be part of this envelope that's been shed, that's kind of come in like a fog, obscured the surface, which makes it appear a lot dimmer. We also know that there's a lot of really crazy magnetic activity going on the surface, and that magnetic activity is not like beautiful, simple bar magnet kind of stuff that we do in primary school science.
Classrooms. Yeah,
these are magnetic fields that are just all over the show. The sun has a crazy magnetic field, but it still has kind of an overall alignment, even if it's got hot spots. But if you take away even the symmetry of this star, and you've got bright spots, you've got plasma moving all over the place, it's just a mess.
Yeah, messy, big,
it's really, really
puffy.
Messy. And then you've got maybe there's kind of some really interesting things going on with the hot spots that are appearing on the surface. These are kind of big areas, like big blobs on the surface that are much brighter or much hotter than the rest of the surface. We think these are something to do with big bubbles of convection that are coming up from and deep inside the star. And then it starts rotating as well, so then those things rotate in and out of your view. So there's lots of wonderful, weird, complex physics going on.
It must take ages for this thing to actually rotate.
That's a good question. I haven't looked at the rotation.
Something that size.
Yeah.
And it may
just by conservation of angular momentum, it must be pretty.
And it may even be for something that complicated. Like, what does rotation even mean?
Yeah.
Something that size.
Well, that's the thing. The whole thing doesn't have to rotate at the same rate. It's probably got a lot of differential rotation.
I'd love to see what this thing looks like. I mean, okay, maybe not quite up close, but I've been looking recently for some other work that I've been doing at some of NASA's solar observatory imagery of the sun. And it's, absolutely staggering. If you've never seen this stuff like this, it's all over YouTube. It's really easy to find. And, daily or multiple times a day, taking these amazing pictures of the sun. And you can see huge, just great explosions of gunk coming off the surface of the sun. And it is roiling and boiling around. It's amazing stuff. I would love to see what Betelgeuse looks like under similar kinds of observational circumstances. Just what the surface of this thing would even look like. Must be amazing.
Yeah, so this whole envelope that I'm talking about with Betelgeuse, its mass that it's shed in previous parts of its evolution, this is probably something like 250 times bigger than the star itself.
Wow.
So if we say that this is about 5 astronomical units,
Yeah.
250 times 5 is about 1,000 astronomical units.
Which gets us where?
Well, Pluto's kind of at its worst about 50.
Wow. Okay. So this is a star and its sort of shroud that extends well beyond the boundaries of our solar system.
Yeah.
Wow. That's nuts. So
It's
no
huge.
wonder it's a little bit difficult to get a grip on what's happening here. What is this thing doing?
Yeah. So, just some other cool little things about that Betelgeuse. Because it's so big and it's so bright, but it's so red, if you actually had eyes that could see the entire electromagnetic spectrum, the Betelgeuse would be the brightest star in the sky.
Across all wavelengths?
Yeah, because most of its light is
wow.
put out in the infrared.
Ah.
If you could see it, then it would
Then it would be the brightest.
It would just blow you away. You'd be like, "Whoa, what is that thing?"
Wow, cool. Okay.
Crazy.
What else?
So what else have we got? So Betelgeuse is a wonderful word. Let's come back to this.
It is a
the
good
naming
word.
of
I mean,
it.
of all of the names of stars, it's up there and then there's Betelgeuse, and that'll it's just such a nice word. No
Yeah.
wonder they picked it for the movie.
So Betelgeuse is an Arabic word, or at least it maybe once was an Arabic word.
Sure.
You might notice that the stars in the sky have pretty strange names. You might expect them to have Latin names or maybe Greek names.
Sure.
If you're going to go by, say like plants, the plants' botanical names are Latin, for example.
Sure.
And that's true also for the constellations. For example, we basically use Roman and Greek names for planets. So, these do have the similar origins, but stars tend to be, not all, but many of the stars that have proper names are from Arabic.
Yeah. Betelgeuse is not a Roman name. It's not not Greek.
No. And so Betelgeuse itself, the name, means, depending on how you translate, back translate and translate again, either shoulder or, my favourite, armpit.
Oh, okay. So it's not just in our astrological mythology, the shoulder of Orion. It's the shoulder. That's the name of it.
Or the armpit,
Or the
because
armpit.
actually Orion's holding up a club. You might not have thought about that part of the constellation or looked out for it, but his arm is holding up a club while his other arm has a shield.
That
I always thought
wasn't
it was an
aware.
archer, but it's a shield, the other one.
No, it's Capricorn. No, Sagittarius is the archer.
Yes.
Capricorn's the goat.
Yes.
Sagittarius. I should know this because I am Sagittarian, but I don't pay a lot of attention. Yeah, holding up a club. So
He's holding up a club.
Betelgeuse is his armpit.
Yeah.
There you are. A big, red, blobby, hairy armpit.
And this is not super unusual for a lot of the stars that do have proper names, because I'm going to tell you how some of the stars sort of maybe got their names. Actually, how stars got their names is a really complicated field, and I don't want to belittle the enormous amounts of research that go into this, because it's all tied up in culture and linguistics and all sorts of stuff. But
Gone
this
back
is
a very long way.
a very broad brush approach seems to be something like this. So Ptolemy decided to name
That's
some of the stars.
Ptolemy.
Yeah,
Yes.
with a PT. Yeah, Ptolemy named some stars and constellations based on their positions in those constellations. So he said Orion's armpit, or the fish's tail, or the boat's mast, or whatever. Right?
Sure.
And these are not all the same constellations as we have today. Some of them have come and gone, but by and large, in the Northern Hemisphere, that's what happens. These were translated into Arabic sometime in the 8th to 9th century.
Okay.
And Arabic astronomers, or Middle Eastern astronomers in general, were incredibly talented. They were great mathematicians, they were great navigators, and so these things were really, really important.
It's
in
really not
those
appreciated
cultures.
how much stuff happened in the Arabic world in those centuries around science, mathematics, astronomy. It's extraordinary stuff.
I read a whole book once just about the number 0 and how that came about. Amazing stuff. Then sort of after we sort of got over the Dark Ages and kind of reared our heads into the Enlightenment period, somewhere maybe in the 12th century, the Latin, or people who are not Latin, but people in Europe, back translated the Arabic names back into Latin.
Right. Okay.
And sometimes did a very poor job.
Go figure.
So some of the stars' names sort of have some kind of Arabic root that may have come from a descriptive word for where they are in the constellation, at least in the Latin constellation. But the words and the letters kind of got a bit messed around with as well. So they're not direct kind of translation.
So some of the names at least have gone from one sort of interpretation of the night sky through to completely different language and culture, and then around to a third different language and culture, and they're the names that we've ended up with.
Exactly.
Right. Yeah.
So you can actually write Betelgeuse in a word that means a similar thing in a number of different ways and pronounce it in a number of different ways. We've just kind of settled on this particular one because it sounds kind of cool, I think.
Yeah.
Yeah. So that's kind of star names, and then why we have them that way.
All right, so that's star names, but coming around back to Betelgeuse and what it's been doing. I mean, has it been doing this? Has it been changing for a while now? Is this unusual for Betelgeuse? Is it just what Betelgeuse does? Are astronomers surprised by this?
We understand Betelgeuse has actually been a variable star for pretty much as long as we've known it for.
Right.
Betelgeuse is quite a young star. It's only about 10 million years old.
Okay. And again, young in the astronomical sense. 10 million is a lot for us, but not so much for a star.
Yeah. Well, think about our own sun. Our own sun's about 5 billion years.
Billion as opposed to 10 million. So that's a huge difference.
So this tells you about the crazy evolution of very, very high mass stars, right? They burn through their fuel incredibly quickly and evolve. Whereas our star has still got, half of its fuel reserves roughly still left to go. So Betelgeuse has been known to vary for a very, very long time. In fact, its original and its current Bayer classification, which means basically we take the constellation and we number or label the stars from the brightest down to the faintest, and we using Greek numerals because
that's what we do.
So we've got alpha, beta, gamma.
Oh, you use alpha this one. Okay, right.
So
okay.
So Betelgeuse is another name for Betelgeuse is Alpha Orionis. But Betelgeuse is not the brightest star in Orion.
It's not alpha. It's losing its alpha status.
So in the past, probably it was, actually. So normally we have known it to rival Rigel. That's a really difficult thing to say.
Say that rival 5 times.
So we have known it to be of similar brightness to Rigel. And maybe when Bayer was doing it in 1603, it was actually slightly brighter than Rigel. And so it got the alpha. It's certainly nowhere near alpha currently now.
So it would now be, what, at best, alpha, beta, gamma?
Probably even further, yeah.
Wow.
I haven't looked through to see where it would sit in the moment, but yeah, it's a lot further. And then Herschel even saw in the 1800s a very similar dimming of Betelgeuse. So Herschel observed between 1837 and 1839, and he saw that it went from 10th magnitude all the way down to 23rd.
How would they have been measuring that?
Sorry, the 10th brightest star to the 23rd brightest star.
How would that have been, like these days I can imagine you could observe something and go, let's literally measure how much light is coming from that star as opposed to that star. You could do that.
Yeah.
In those days, were they just going, that one looks brighter than that one?
Yeah, you had calibration. So you knew that Rigel was this number. So if it changes compared to Rigel, because Rigel doesn't tend to change, then you say, well, okay, it's fainter than Rigel, but it's brighter than Bellatrix, and it's brighter than this, and it's fainter than this.
Right,
so you can,
okay.
And actually, amateur astronomers, even to this day, have very, very good, strong abilities to do brightness measurements by eye. I've heard of observers for the AAVSO, which is the American American Association for Variable Star Observers. There are still professional observers there who are crazy good at getting magnitudes of stars just by visual observation.
That's amazing.
Yeah, you can train yourself to be incredibly good at this. And so but Herschel also had his telescopes, of course, as well. So he was able to look at even fainter things.
Even so, I mean, comparing things which aren't directly right next to each other, that's still not an easy thing to do. Anyway, okay, let's say you can do that.
People were good at that. And that, even going back to people like Goodrich, who was observing eclipsing binaries, this is what they did. They looked at the brightness compared to other objects.
Cool.
So Herschel observed in the 1800s an enormous change in Betelgeuse's brightness. And he also interpreted that as something to do with its evolution. So I don't think he went as far as saying it's going to blow, but this leads us to believe that Betelgeuse has pretty much been coming and going for a very, very long time.
Been doing this for a
while.
So
about 1 million years.
So recent reports of Betelgeuse about to go kablooey any day now, you not so much. Take that with a grain of salt.
No, and it's definitely not our number one candidate at the moment. Anyway.
Which implies there is a number one candidate.
Well, it depends on who you talk to.
Okay, well, I'm talking to you.
My information sources tell me.
My insider sources.
No.
In the Bureau
my
of Supernovas.
understanding is that maybe something like Eta Carina is a better kind of first option.
Okay.
But Eta Carina's also done some very calm things over the last sort of few years, so maybe it's gone off the charts.
Ridiculously calm. But I mean, is that what people look for? Is this star is doing crazy stuff, therefore we think it's about to explode?
Yeah, we don't really know exactly what's going to happen in the sort of moments before a star goes to a supernova.
There haven't been terribly many observations like that, I guess.
Well, yeah, and the observations we have generally been of very, very faint things.
Mm-hmm.
And you don't know it's going to go until it goes, and then you've got to go back into your data and then see,
what did it
look like
yesterday?
before it went?
Yeah.
And did we have observations of it, say, in the last year? Maybe we didn't. So it's not an easy science to do. 1987A, the supernova, which was in the Magellanic Cloud, was probably the closest good observation we have of that. But then that's still getting on to nearly 40 years ago.
Yeah.
So
yeah. And even if you're talking about something which, best candidate for blowing up, it could happen anytime within the next couple of 100 years. It's really hard to get that amount of observing time, I would imagine. We just want to lock on this
grant
thing.
proposal will be.
We just want to lock on this thing for the next, let's call it half a millennium. Okay? Is that all right? Okay with you?
Indeed. So it's not super accurate science.
Right. Yeah.
But that being said, I think Betelgeuse exploding would be very, very cool. We'd be, first of all, completely safe.
Good. Okay.
600 light years is a really nice distance to live from a supernova.
It's far enough for it to be interesting but not deadly.
Exactly. Yeah. So we wouldn't get kind of the really huge amounts of radiation of gamma rays, X-rays, ultraviolet. Would be fine. It's a long way away. That would all kind of, we'd get some, but it wouldn't be of that nature.
Just out of curiosity, I do believe we have talked about this before, but let's say the closest star to us, other than the sun, which is, remind me, what's
Proxima
the next
Centauri.
Okay, yeah. Yep. Let's say that one went supernova. Forget about the fact that it may not be the right kind of star to do that. Let's say it did. How bad would that be?
Pretty bad. Yeah.
As in we're done.
Yeah.
Kind of bad.
That's a radiation complete sterilization.
The next
of the planet.
star, that's a really long way away, but that's a lot of wow. Okay.
Yeah. So that's
Supernovas are big, aren't they?
They're pretty big.
They're not mucking around. Supergiant supernova. We're getting a sense here that in astronomy, super means we're not mucking around. This is big.
Yeah.
Yeah. Okay. So, but Betelgeuse is far enough away that it would be spectacular, but not dangerous.
It would look really pretty.
What would it look like?
So it probably means that Betelgeuse would look like something in the sky that's probably brighter than the full moon and very, very likely to be visible during the day.
Brighter than the full moon. Wow. I mean, I guess it would take a while for it to actually, like you see sort of images of nebulae and so on, which have been, supernova that's then been expanding out all the time since. So it would take a while for Betelgeuse that explosion to sort of spread out.
It would,
So we would still see it as very, very small, effectively point-like star-like, just really bright.
Yep.
It wouldn't become big in the sky, just bright in the sky.
Exactly, yeah.
Wow.
But once you sort of waited a few thousand years, then you'd get some really nice nebulae from the telescopes.
So I guess when we get to the end points of some of these conversations on this podcast, we invariably come around to the same question, which is, so Emily, from an astronomical point of view, why do we care about this? What's important in this story?
Well, I've got two things.
Go on then.
Very, very different things. One is the science that's going on, and I think that's really exciting. We're so lucky to have the Orion Nebula close to us. We can see the birth of new stars in this kind of stellar nursery environment. We're also very lucky to have stars like Betelgeuse close to us because we can see the deaths of stars happening, and we can see the disk of Betelgeuse. We can observe these brightness changes. We can observe spots on the surface. That's really exciting. So all this information is telling us more about the physics that go on in stars and that play out from their birth all the way through to their death.
So the fact that we've been observing Betelgeuse doing its crazy thing over the last however many months, if you take away the alarmist, it's about to explode, and it's like, well, let's shelve that for a minute, it's still really good stuff.
Yeah, it's fantastic. And so we're going to learn a lot from all our observations of Betelgeuse now and in the future about how these very rare, very, very massive stars live their lives. But I think even more kind of exciting than that is that Orion's a really easy to identify constellation in the sky.
That is true. I mean, if you were to ask people to go and find Orion, I would say a large number of people, I don't hesitate to say maybe most, would be able to do that.
It's visible from nearly the entire planet because it's very, very close to the equator, the celestial equator. It's observable for several months of the year, generally January through to March. So now's a really great time to go out and see Orion because the sun's opposite part of the sky, if that makes sense. And yeah, there's enough bright stars that are in a strange enough shape that it's easily identifiable.
Yeah.
And so you can go out tonight or tomorrow or the next night that it's clear and see the evolution of stars happening live in front of your eyes. You can see that Betelgeuse looks a lot dimmer than Rigel and Bellatrix and so on that are around it. And that's crazy.
Yeah, whereas it used to be, not so long ago in human terms, it used to be the alpha, used to be the brightest one in that constellation. It's now clearly, demonstrably not.
Yeah.
That's change.
And in a few months' time, it may well be back to being nearly the same brightness as Rigel.
Yeah, and you could even train yourself to even observe that for yourself. If other people can do it with their eyes, you can.
Yeah.
There's a challenge for this year, for 2020. What New Year's resolution did you make? My New Year's resolution is to be able to spot when Betelgeuse gets brighter again.
That's a fantastic resolution.
I like it. Well, finding our way out of this super big episode of the Syzygy podcast. First back for 2020, which is very exciting. And my brain has been blown. I think, often on this podcast, I find my perspective on the universe being shifted somewhat. And the notion of a star roiling around at a size somewhere between the asteroid belt and Jupiter has just really thrown me for a loop. Along with what a supernova would actually mean on a star fairly close to us. But, that's okay. I'll come to terms with that. Emily, good to be back.
It's fantastic. I'm so excited. There's been so many new discoveries that have come out over the past few weeks, and several of them will be like, oh, that would be great to talk about. And I was so excited when you suggested this one. So I was like, oh yeah, Betelgeuse is great. I love Betelgeuse.
It's a good one. I'm glad we did this one as well, because I didn't really know anything about Betelgeuse other than it helped to name a movie. We have had a few suggestions thrown our way from listeners, and by listeners I mean my mum. So we're able to start filling up the whiteboard here in Emily's office. But if you out there in listenerland have any thoughts, suggestions, comments, questions, ideas, then there are a bunch of different ways that you can get in contact with us. Emily, name one.
Twitter.
Yes.
Yay.
How do they find us?
We are at SyzygyPod. And we are you type in SyzygyPod into Facebook. Yeah. You can get us up on Instagram. You can even get to our fantastic website, syzygy.fm.
That's right. I think we've probably been a little bit quiet on the social medias over the Christmas period as we've been eating you had lamb, I had goose, which was rather nice over Christmas, which is good. But yeah, we've been a bit quiet on the social media, so it's time to ramp that one back up again for 2020. You can find us out there on the interwebs in those ways. There are other ways that you can get involved with this podcast other than sending us questions and ideas and comments and hellos and emojis. One of those ways is to help us out, to help us rise up through the noise of the infinite number of podcasts out there on the interwebs. The best way to do that is to just tell people, go and tell people about this fabulous thing that you've been listening to as you've been doing the vacuuming around the home.
And tell them about Betelgeuse.
That's right.
You'll impress all your friends.
Take them outside and point it out to them and say, that one there, it's going to explode any minute now. No, don't tell them that. That would be wrong. Leave a review on your podcast client of choice. Give us a few stars and a bit of a comment and a review, because that really does help us to rise up. Every single one of those comments helps us to move through the noise. And you can, of course, contribute financially to help us keep the lights on here in Syzygy HQ by going to patreon.com/SyzygyPod, of course. But otherwise, that brings us to the end of the first show for not just 2020, but for an entire new decade. Very exciting. So we'll catch you in, a week's time or so. Catch you later. Bye, everybody.